The fourth topic is phase sequence. The phase sequence is a sequential order at which the voltage passes to the zero phase point or the point of maximum voltage. Phase sequence in three-phase system determine the direction of rotation of three-phase induction. Phase sequence also decide whether we can connect one three-phase system parallel with another. So we have the phase diagram, and we also have the voltage A, voltage B, and voltage C. And we have a 120-degree in every angle. The total of angle of this diagram is 360 degree. So I will put a line here that indicate the zero phase point or the point of maximum voltage. So our rotation is counterclockwise. So kapag umikot ito, ang unang matatamaan ay voltage A. Kapag nag-rotate ulit, pa-counterclockwise, ang matatamaan naman ng ating zero phase point or point of maximum voltage ay ang voltage B. And then, kapag nag-rotate na naman ito, ang huli nating matatamaan is the voltage C. So, the sequence of this is ABC sequence, also called as positive sequence. So, there is reverse rotation too, and it's called clockwise rotation. Clockwise rotation. So, kapag pa-clockwise rotation naman tayo, ang una pa rin matatamaan ng zero phase point ay ang voltage A. Ang susunod na matatamaan kapag pa-clockwise ay ang voltage C. At ang huling matatamaan ng zero phase point or point of maximum voltage ay ang voltage B. So, this sequence is called ECB sequence or also called an negative sequence. However, it is usually practiced to name the three-phase or winding after the three natural colors R red, Y yellow, and B blue. So for this case, this is the R red, Y yellow, and B blue. Katulad din ng nasa taas, it has 120 degrees and the total angle is 360 degrees. So, kapag pa-clockwise ang rotation ng ating diagram, ang magiging result nito ay R, Y, B. At ito ay positive sequence. Kapag clockwise naman ang rotation nito, ang magkakaroon tayo ng R, B, and Y. At ito ay negative sequence. The fifth topic is interconnection of the three phases. Interconnection of the three phases, star or WYEN connection and delta connection, are the two different methods which are used for connecting three-phase system. In this topic, we'll learn in detail about the star and delta connection. We'll also know voltage and current relationship in both the connection and where these connections are used. And this topic will also have a look at power transmitted by these two types of connection. Connection shown in this figure is one of the ways to connect three-phase generator to the load. As you can see, this connection requires 6 wires to connect. The three single-phase circuits shown in this figure are electrically independent, but if you observe the image carefully, you'll find that we can combine the three return conductors together to form a single return conductor. By doing this, we can have a safe cost of conductor as the number of conductors are reduced from 6 conductors to 4 conductors. Now, this common return conductor is called as neutral conductor. It carries sum of three current IA plus IB plus IC. At first, many people think that the conductor required for neutral should be 3 times in the size than the other three conductors. But as we know, current of the three phase are out of phase by 120 degrees from each other, and if we draw a waveform or this current, it will look like this. Now, if you observe the diagram carefully, you'll find that the sum return current is zero at every instant. For example, at instant corresponding to 240 degree, IC equal to Imax and IA equal to IB equal to negative 0.5 Imax. So if we add this return current, we'll get the sum we'll get the sum equals 0. And this is the true for every instant. We can remove a neutral conductor without affecting the voltage or current in the circuit. So if we have reduced the number of conductors 6, which was the initial stage, to 3, 50% saving in conductor cost. However, the load shown in the circuit must be identical if you want to remove the neutral conductor. If your load is not identical, then remove neutral conductor can cause an equal voltage across the load. So in an ideal situation or in the situation where load is equal, correct flowing through neutral conductor is 0. The condition where load is not equal and neutral must be provided. You might have heard people saying 3.5 core cable that 0.5 core is your neutral conductor. The circuit shown in the figure called as three-phase three-wire system, the generator and the load are said to be connected in WYE as it resembles the letter Y, or the some people called it as star. The figure shown as the three-phase four-wire system. The neutral conductor can be similized or maybe slightly smaller than the other conductors. Three-phase four-wire system is widely used to supply power to commercial and industrial customers. Now, we have to talk about the star connection. Three-phase system, there come two concepts, line-to-line voltage and line-to-neutral voltage. The voltage between A and N, this is called as line-to-neutral voltage. Similarly, voltage between A and B as line-to-line voltage. Relationship between this voltage as well as current change with the type of connection, so it is important to consider this relationship for different connection. In case of star connection system, line-to-line current are equal to line to neutral current, but in case of voltage is different. Consider that the winding shown in this figure, which is connecting in the star, as you can see, the conductor are placed 120 degrees apart from each. So if you can apply Kirchhoff voltage law to this circuit, by doing some mathematical, you'll find that the line to line voltage is therefore root 3, the line to neutral voltage, so you can write EL, this represent value of the line voltage, equal the root 3 times ELN, which is the line of neutral voltage. Next is delta connection. The other way to connect three-phase system is called the delta connection. The connection is so named because it resembles the Greek letter delta. Let's have a look at the voltage and the current relationship in the delta connection. How in case of delta connection, voltage across each connection is same as the line voltage. But in case of current across each element is different than the line current. If we can apply the Kirchhoff law and do some math, you'll find that the line current in root 3 times greater than the current in each branch of delta connection system. Generally, star connection is used where you need a neutral and two separate voltage like other distribution system. Delta connection is the generally prepared where neutral conductor is not needed, like for transmission or high voltage power. Also, delta connection is prepared when third harmonic need to control. Star and delta connection are almost used everywhere when we talk about three-phase system. You'll generally find three-phase transform connected in different combination of star and delta connection. For example, Star Connect transformer is generally used in an autotransformer. Delta connection transformer is generally used for high voltage transmission. Multi-star connection transformer is generally used as distribution transformation. Power transmitted by star and delta connection. Now, as we have studied the star and delta connection, a question can pop up: power transmitted by a star connection and power transmitted by a delta connection is the same or different. So let's find out. Consider the star connection winding phase. Apparently, power transmitted by a single phase is given by this formula. This is the power transmitted by a single phase. To calculate the power transmitted by three phase, we can multiply this equal by 3. So the result will be this. Similarity, apparently power transferred by a single phase delta connection is given by this formula. Multiply this equal to calculate power transmitted by three phase and you'll get the same result as the star connection. And this proof power transmitted by the both connection is the same. So let's summarize it. Three-phase system can be connected in two different star or delta. In star connection, line-to-line current is equal to line to neutral current, but in line-to-line voltage is root 3 times the line to neutral voltage. In delta connection, voltage across each element is equal to line voltage, but line current is root 3 times the current flowing through each element. Power transmitted by both the connection is the same. The last topic is balanced three-phase system. A balanced three-phase supply system, star or delta connected, is one in which the three-phase voltages are equal in magnitude and frequency but displaced 100 degrees from one another. The same is true where regard to line voltages. All electric companies make effort to ensure the availability of three-phase balanced supply all the time. There are two types of three-balance load: star-connected load on the left and delta-connected load on the right of the picture. The three-phase load, star or delta-connected, is said to be balanced if the load in each phase is the same. Load in each phase has the same impedance and power factor. If a three-phase load, star or delta-connected, does not meet any one of the above requirements, it is said to be unbalanced. A three-phase star-connected alternator may be connected to a WYE-connected or delta-connected load. Similarly, a three-phase delta-connected alternator may be connected to the WYE-connected or the delta-connected load. So, for this three-phase Y-connected load, ang role ng line current, so ito yung line current. Ang halimbawa ng line current dito sa diagram ay ang IA, IC, at IB. Ang phase current naman, ito yung dinadaanan ng flow ng line current. At ito ay ang IA, IB, at IC. Kung susundan natin ang flow ng line current na IA, ito ay dumadaan sa phase current ng IAM. Sa ganung process din, ang IC, dumadaan din ang flow dito sa phase current ng ICM. Sa IB line current naman, dumadaan ang flow nito sa IBN phase current. Kaya connected ang load ng line current ay always na equal to phase current. Next is IN equals to 0. IN represent the neutral current. Kapag ang neutral current natin ay 0, ibig sabihin nito hindi na natin kailangang maglagay ng neutral conductor kasi perfectly balanced na ito or equal na sa 0. Pero dahil hindi naman always sure ang distribution load is balanced, kaya maglalagay pa rin tayo ng neutral current to carry yung neutral current. Next is line-to-line voltage is equal to square root of 3 times the phase voltage times the 30 degree. Next is S, or apparent power, is equal to square root of 3 times the line-to-line voltage times line current. Pagdating naman sa 3-phase power is equal to 3 times the single phase power. Sa delta connection load, ang phase current nito is laging equal sa line-to-line voltage. So, ito yung mga line-to-line voltage. For example, dito ay ang IAB. Ang voltage na nagko-cross dito ay ang voltage across A at ang voltage across B. Pagdating naman sa IBC, ang nag-a-across is voltage C at voltage B. Sa ICA naman, ang nag-a-across ay ang voltage A at ang voltage C. So, delta connection load, ang line-to-line voltage is phase voltage lagi. Pero ang current nito ay nag-iiba. So, kapag in-apply natin ang Kirchhoff current law sa load A, ito, ano nga ba ang Kirchhoff current law? Ito yung sum na current na pumapasok sa load is equal to the sum of current na lumalabas sa load. I mean, sa disabled load. Halimbawa nito ay ang load A. Ito, load A. Ang pumapasok dito ay ang IA at ang IC. At ang ang lumalabas naman na current sa load na to ay ang IAB. So, IA plus ICA is equal to IAB. So, ang kinukuha nga natin na current ay ang IA. So, IA is equal to IAB. Ngayon, itatranspose natin itong ICA sa kabilang equation. So, magiging minus ICA na siya. So, next is load B naman. Sa load B, ang pumapasok na load is ang IB. At ang IAB. At ang lumalabas naman sa load na to ay ang IBC. So, IB plus IAB is equal to IBC. So, ang hinahanap naman natin dito ay ang IB. Ito. So, IB is equal to IBC. Ngayon, itatranspose ulit natin tong IAB sa kabilang equation. So, magiging minus IAB. Next is load C. So, ang pumapasok sa load C natin is IC. Tapos, ang pumapasok pang isa is ito, IBC. Ang lumalabas naman na current sa load is ang ICA. So, IC plus IBC is equal to ICA. Ngayon, ang hinahanap natin sa load na C ay ang IC. So, IC is equal to ICA. Ngayon, itatranspose natin itong IBC. So, magiging minus IBC. Next is yung formula naman sa delta connected load. So, line-to-line voltage is equal to voltage phase, and then sa line-to-line current is equal to square root of 3 times line phase times negative 30 degree. Sa S naman, or apparent power, sa S naman is equal to square root of 3 times the line-to-line voltage times the line current. Dito naman sa 3-phase, ito is equal to 3 times the single phase. So, ano nga bang apparent power? So, sa power system load, meron tayong tinatawag na power triangle. Ito yun, power triangle. So, S is apparent power. Nag-i-express ito sa volt ampere, kilovolt, volt ampere, tsaka megavolt ampere. Pagdating naman sa P, or true power, ito ay watts, kilowatts, at megawatts. Pagdating naman sa Q, ito ay reactive power, nag-express naman ang volt ampere reactive, kilovolt ampere reactive, at megavolt ampere reactive. So, ang relationship niyan is S equal to square root of 3 times line-to-line voltage times line current. Katulad ng nasa kaninang formula, ito yun. So, next is P. The P is true power. Pag kinukuha natin ang true power, ang formula niya is square root of 3 times line-to-line voltage times line current, tapos cosine theta equals to S represent the apparent power times cosine theta. Or yung cosine is power factor. Next is Q. So yung Q is represent as reactive power. So Q equals to square root of 3 times line-to-line voltage times line current times sin theta equals to S, or the apparent power times sin theta. Next is ito. So kapag i-represent naman natin ito sa apparent power in rectangular form, S is equal to P plus JQ. In terms of magnitude naman, S is square root of P square plus Q square. So kapag pinagtugay na, ito ang magiging result. So yung total P, ito, is equal to P1 plus P2. P1 is represent, ito yung P1, nakuha natin P1 dito. So, 400 kilowatts plus P2, ito yung P2, 135 kilowatts. Ang magiging total P natin ay 335 kilowatts. Next is Q. So, ang total Q is equal to PQ. Total Q is equal to Q1 minus Q2. So, yung Q1 natin is ito. Ang Q2 is ito. So, Q1 is 300 minus 65.4 kilovolt ampere reactive. So, ang total Q natin is 334.6 kilovolt ampere reactive. Next. Sorry. Next is yung hypotenuse ng triangle na nabuo with the total power. So, yun naman ang ating apparent power. Total which is equal to square root of P2. Total square. Ito yun. Total square plus total Q square. So, apparent power or total S is square root of 535 to 535 square plus 234.6 square. So, ito, nakuha siya sa nauna na 535 kilowatts at 2346 kilovolt ampere reactive. Yun. So, magiging equivalent ng ampere power total natin is 584.2 kilovolt ampere. Next is Ito, power factor total or the total of power factor. So, power factor total or total power factor equal to total P divided by the total S. So, yung total P natin na nakuha natin kanina is 535. Tapos, yung total S naman natin is 584.2. So, pag dinivide natin ito, ang magiging total power factor natin is 0.916 lagim. So, yun. So, ang final answer natin for this one, for this, determine the power factor of combined motor load is 0.916 lagim. So, next is kasi naman. The pag-calculate ng magnitude of line current delivered by the source is ito. Ito ang magiging formula natin. S is equal to square root of 3 times line-to-line voltage times line current. So, ang hinahanap pala dito sa C ay line current. So, magta-transpose lang tayo. Line current is equal to S divided by the square root of 3 times line-to-line voltage. So, IL is equal to 584.2. Ito yung S. Ita-times natin siya sa 100 kasi ang volt natin is nasa 1,000 plus. So, divided by the square root of 3 times 4,160. Ito yun. Ayan. Ito yung line-to-line voltage natin. So, ang magiging line current natin, the final answer for letter C is 81.08 ampere.